Since today is the last class, I'd like to at least give a brief overview of the techniques that one can use to solve constrained optimization problems. So far, we've mostly focused on unconstrained optimization problems or algorithms for unconstrained optimization problems. We saw one general approach for solving constrained optimization problems, which was using KKT conditions, right? But then in practice, you have to solve those numerically. Sometimes you can find closed form expressions using KKT conditions, but that's not always the case. So what do you do? What kind of approaches can you use? We've seen one class of approaches, which is projected gradient descent, uh, but but that's not always feasible. It's not easy to implement projected gradient descent in all scenarios. Particularly the example that you've seen in the fourth assignment. It's difficult to do the projection step unless you have some other approach to find it. But in certain cases, for certain problems, you can either find a closed form expression for the projection step, or there are ways to implement certain projection steps very efficiently, depending on what your constraint set is. Right? So how do you solve constrained optimization problems? So the first approach is something that we've already seen, so I'll just briefly overview that. The first is projected gradient descent. So what is the projected gradient descent method? Again, the goal is to solve an optimization problem of the following form. So minimize some function f of x subject to the constraint that x lies in some feasible set f. Right? This feasible set could be defined, either it could be given to you in some geometric manner, or it could be defined using a set of inequality and equality constraints. So the projected gradient descent does the following. So you initialize some vector x0 and for t steps you run the following. So you define an x tilde t to be equal to xt minus some delta t gradient f of xt. Right, that's the descent step. And then this particular x tilde t may or may not lie within the feasible set, so you project it back to the feasible set. So x t plus 1 would be some projection of x tilde t onto the feasible set. How do we define this projection step? There are a number of ways to do it. The most standard way to do it is use a minimum Euclidean distance projection, if that makes sense. This is the arg min. x lying in the feasible set of x minus x tilde t. More often than not, you'll use the squared Euclidean distance, but it doesn't matter. But more generally, you could use any distance or divergence. Our only goal is to ensure that xt plus 1 lies within the feasible set. Okay. Most often, you use the minimum Euclidean distance, but for certain kind of problems, you may want to use a different divergence or a different distance. Perhaps one that lets you obtain a closed form solution. Right? In the assignment, you would have, there's one problem of finding the minimum KL divergence projection onto the simplex. Finding the minimum Euclidean distance projection to the simplex is hard. There is no closed form solution to that. You can do it numerically, but finding the minimum KL divergence projection, you can get a closed form expression. Right? So you may want to go for that instead of minimizing the Euclidean distance. Right, so that's the projected gradient descent method. For certain kinds of sets, you can find closed form expressions for the minimum distance projection. Right? So here is an exercise problem. Suppose you are given an optimization problem of the following form. Yeah. Okay. I'm sorry, what was 4.2? It was using what? You mean to say, I think that was using the water filling method, right? Sure. So basically, you know what the water filling solution is. Everything is there. You have an expression, except you have to find lambda, right, or lambda star. You have to just find lambda star numerically. No, write a program. Write a program. You can't get a closed form expression to do it, right? So you write a program. You search. It's basically a search problem to find lambda star. Okay, so here's an exercise. Suppose you are given the problem of minimizing half x transpose qx, where q is symmetric and positive semi-definite. In fact, let's assume that q is positive definite. And yeah, if you want, you can also assume that for the purpose of this question, or at least part of the question, assume that q has distinct eigenvalues. Okay, so you want to minimize this subject to the constraint that the L2 norm of x is exactly equal to 1. Okay, so it's a quadratic optimization problem with a quadratic constraint. Is this a convex optimization problem? Think carefully. How many say yes? It is a convex optimization problem. How many say no? It's not a convex optimization problem. Only 2. Your exam is next week. Okay, if it is not, why is it not a convex optimization? constraint set is not convex. If this were L2 norm of x less than or equal to 1, then that would be a convex set. But this is a set of all x for which the L2 norm is exactly equal to 1. Right? So it's not a convex optimization problem. You can still use gradient descent or any approach you want. It doesn't mean that it will give you the correct solution. It may or may not give you the correct solution, but you can still apply it. Right? Okay, so this is the constrained optimization problem. So the exercise is find an analytical expression. Okay, so first, even before that, find the projection step. Right, so in other words, how do you project an arbitrary vector onto this constraint set? You can get an analytical expression for this.
Projection criterion is
Euclidean distance, minimum Euclidean distance projection. Alright? And suppose you were to use projected gradient descent, find an expression for xt plus 1 in terms of xt. Alright? Again, you can get a closed form expression for this. Yeah. In PCA, the goal is different. So typically, the goal is to maximize x transpose AX. So as I said, so if you wanted to find x, okay. So Q is positive definite, right? Some positive semi-definite matrix or positive definite matrix. If I were to ask you, so if you just look at this expression, what do you think the solution should be? Can you be more specific what the solution will be? Again, look at the question carefully. Yeah?
the eigenvector normalized as the highest eigen.
Again, look at the question carefully. What are you trying to do? Yeah. So the solution is the smallest eigen of the minimum will correspond to half the smallest eigenvalue of Q, and the minimizer will be any eigenvector that corresponds to the smallest eigenvalue. Right? In PCA, typically it's the other way around. You want to maximize this particular quantity. Right? So this is different. That itself should let you guess a lot of these solutions, the solution to this. But for whatever reason, I want to do it using this projected gradient descent approach. Okay? And it will turn out that this gives a kind of a natural algorithm to find the corresponding eigenvector. Okay, so the third question is, which one? Yeah, I'm assuming the Q is symmetric and it's positive definite in this case. I want positive definiteness because I want this to be convex, the objective function to be convex.
Sir, will we lose generality if we assume Q is
diagonal with distinct non-zero entries, positive distinct non-zero?
In what sense will you lose?
Because that is PD and any PD is diagonalizable with distinct diagonals.
Correct. I mean, in what sense are you asking if we lose generality?
In the sense that I transform my coordinates,
Okay.
right? So X is transformed to this.
Sure. In principle, yeah, you could do that because Q is fixed; it is given to you.
But this L2 norm X equals 1 would be something else, right?
That doesn't matter. You can, because since Q is symmetric, it is orthogonally diagonalizable. So what you're doing is an orthonormal transformation, which does not change the norm of. Instead of looking at, so you could write Q as some A transpose lambda A, where A is an orthogonal matrix. So the norm of AX would be the same as norm of X. So you wouldn't be losing out much, but it doesn't matter. You don't need to do that.
Condition Q is
Symmetric.
symmetric, right?
As long as Q is symmetric, it's enough.
PD doesn't imply symmetry.
It is, right? So it's symmetric positive definite. Whenever I say positive definite, the underlying assumption is that it is symmetric. Right? I mean, not all of these sub-questions require it to be positive definite. It's just makes life easier. Okay, the third question is projected gradient descent assuming that delta is sufficiently small, under what conditions is this guaranteed to converge? Conditions on x0, the initial point. All right. So first, what do you, if you had to guess how the projection step would work, can you say something? What would be a natural guess? So basically, what I want is arg min. So you're given a vector, let's say y. You want arg min either L2 norm or L2 norm squared, such that norm of x is equal to 1. What do you think this would be? Yeah, y by norm of and y. Yeah, so the geometric way of seeing it. So suppose you are given an arbitrary vector let's call this y, right? You want to find the minimum Euclidean distance projection to this set. Then pictorially, if I just had to draw this, which would be the projected point? Yeah, exactly. So it would be the point at which this line meets the circle, and this is nothing but y by L2 norm of y. The same holds even if y is inside the circular region. That's a geometric explanation, but you can also use, let's say, the KKT conditions to find this, and you should end up with the same solution. Remember, you're using the KKT conditions even though the problem is not a convex optimization problem. So this is a case where you can do the projection step easily. All right, you can also find the projection onto the entire unit ball. Right, so we have a less than or equal to instead of equal. In this case, the solution will be a bit different. It will turn out to be y by norm of y only if the norm of y is greater than 1. If it is less than or equal to 1, it will just be y itself. Okay. That's again a natural guess, just by thinking about the geometry of the set. This requires some working out, but it's also easy to get a closed form expression for the projection onto any vector space, vector subspace, or affine space. Projection onto a subspace you've already seen. You should have seen it in your linear algebra course. But it's not difficult to just extend this to an affine space, right? And this is a different way of getting it by using, you can just solve this using KKT conditions. Finding this projection becomes harder if you have linear inequality constraints. That's not easy to do. You can't get a closed form expression in general, but if you have equality constraints, then you can get a closed form expression. So that's one approach for solving constrained optimization problems. But it's only in certain special cases that you can do the projection step efficiently. If you're able to do the projection step efficiently, then great, go ahead. You can also derive good convergence properties and so on. But what if you're not able to do this projection step efficiently? What if your set is complicated? Then one approach that you can use is the following. So this is the Lagrangian base method. So when we were deriving the KKT conditions, so how did we get the KKT conditions? It was basically by observing that the solution x star, lambda star, nu star would correspond to the saddle point of the Lagrangian, right? And basically you try to run something like gradient descent to now find the saddle point instead of a local minimum or a local maximum, right? So if you think about it, the Lagrangian, so again we are assuming that, let's start with a simple equality constrained problem, or let's start with something more general to just give you the general idea. So we want to minimize f of x subject to a bunch of inequality constraints and a bunch of equality constraints, right? So the Lagrangian comma nu, the solution of the KKT conditions would be x star, lambda star, nu star, and this Lagrangian is essentially convex in x. If it's a convex optimization problem, it's convex in x and concave in lambda and nu, right? So one way to search for a solution is to run gradient descent for x but gradient ascent for lambda and nu, right? So basically you try to maximize with respect to lambda and nu, and you try to minimize with respect to x, and you do it alternately. So let's do it step by step. Just equality constraints. So suppose you had to minimize f of x subject to hj of x equal to 0, 1, 2, 3 up to n. All right. Now there are no constraints on. Okay, so you have the Lagrangian. This is equal to f of x plus, I can write this as summation j equal to 1 to m hj of x times nu j, or I can also write it in the following vector form. Vector nu transpose vector h of x. Right? So what would gradient descent with respect to x look like? It would be this minus some delta t times the gradient of L with respect to x, right? gradient is taken with respect to x. What is that equal to? Yeah? Can you speak up? I can't hear you. Okay, it will be gradient of f plus. But I want it in terms of, so you can think of h as a function from Rd, assuming that x lies in Rd, to Rm. Right? So what would it be in terms of dh, the derivative of h, or the derivative of h with respect to x? What are the dimensions of the derivative of h with respect to x? Yeah? It will be an m cross, it will be m cross d, because I'm assuming that x lies in Rd. So this should be dh transpose of xt times right. So dh transpose is a d cross m matrix. It's evaluated at xt, and this times nu t is going to give me a d length vector, column vector. So that's the update step for xt. What would be the update step for ut? Yes. This shouldn't be difficult. I'm sorry? How do you choose nu? Nu is the Lagrange multiplier, right? My goal is to find that value of x comma nu which corresponds to a saddle point of the Lagrangian. Some delta t prime, we could use a different step size. H of xt minus which direction should you be going? Should you be ascending the hill or descending the hill?
Because it's concave, you ascend.
Yes, so it's going to be plus. You want to move in the direction of the gradient. not in the direction of the negative gradient. Right? Because you're trying to maximize. So suppose you take this algorithm, you start with an initial point and you run it until maybe it converges. Right? So I'll say that. So firstly, just definition. Some x bar nu bar is a fixed point of this algorithm if you set xt equal to x bar and nu t equal to nu bar, then xt plus 1 is also equal to x bar and nu t plus 1 is also equal to nu bar. So basically, if you try to take this to be equal to xt, then it doesn't change. Right? There's no point in proceeding with this iterative algorithm anymore. The point here is that if suppose you started with the convex optimization problem and you ran this algorithm and it happened to converge. Now this algorithm is not guaranteed to converge, but if it so happens that it converges to some fixed point, then this fixed point would actually be your solution. Alright, because the only fixed points you can have are those which satisfy the KKT conditions. It's fairly easy to see that. Suppose that some x bar nu bar is actually a fixed point of this equation, of this set of equations. Then what would happen? Xt plus 1 would be equal to xt and nu t plus 1 would be equal to nu t, which would mean that this quantity should be equal to 0, right? Because otherwise you can't have xt plus 1 equal to xt, and this quantity should also be equal to 0. Otherwise you can't have nu t plus 1 equal to nu t. But what does it mean? This equal to 0 implies that the constraints are satisfied, and this equal to 0 means that it's a stationary point. Right. And that means that all of the KKT conditions are satisfied. And likewise, if the KKT conditions are satisfied, then this quantity is equal to 0 because it satisfies h of x equal to 0. And this is also equal to 0 because if the KKT conditions are satisfied, then it's also a stationary point. And that means that xt plus 1 should be equal to xt and nu t plus 1 should be equal to nu t. Right. So this algorithm is not guaranteed to converge, but if it converges, it will converge to the solution, the correct solution. Right. But one thing to keep in mind is that unlike projected gradient descent, where at each step you're enforcing that xt satisfies the constraints, here you don't have such a guarantee. It is possible that xt at some point does not satisfy h of xt equal to 0. Alright, so that's something to keep in mind. So the quality of, so if you ran this algorithm for a certain number of steps, then there's no guarantee that the final solution that you get will even satisfy the constraints. You can do something similar even for the case where you have inequality constraints. All right, but it look a little bit different. So suppose you want to minimize f of x subject to just inequality constraints, gi of x less than or equal to 0, 1, 2, 3, up to n. All right, and so the Lagrangian can be written as f of x plus, again as we did previously, I can write this as g of x transpose lambda. So once again I can write xt plus 1 to be equal to xt minus delta t times gradient of L with respect to x evaluated at xt lambda t, which is nothing but gradient f of xt plus the derivative of g evaluated at xt transpose lambda t. Right, so that's that would be the update rule for xt. But what sort of an update rule do we choose for lambda t? Lambda t plus some delta t prime g of xt. It's one way to do it. But now I can't guarantee that at every step. Remember that when we talk about the Lagrangian, we're always assuming that lambda is strictly greater than 0. Right? So that's a constraint. In fact, when we're trying to solve for the stationary point, it is under the constraint that lambda is greater than 0. So it's not enough to just do this. I also have to project it back to the constraint set. And this happens to be plus delta t prime g of xt, the positive part. So basically, if you take a number, the positive part of this number is just max of v comma 0. So here's another exercise. If y lies in that range, it will be just that itself. Correct. Yeah. It's axis aligned. Yes. Yeah. So this it will just amount to a coordinate-wise mapping of y to something. So basically, if yi lies between alpha I and beta I, then xi should be equal to yi. If it is less than alpha I, then you set xi to be equal to alpha I. If yi is greater than beta I, then you set it to be equal to beta I. So in this case, the projection is very, very easy to implement. And again, we also have the same point that if x bar lambda bar is a fixed point, then KKT conditions must be satisfied. This requires a little more thought because I have this plus over here, right? So suppose that it satisfies the KKT conditions, right? What does that mean? So firstly, if the KKT conditions are satisfied, then it satisfies the stationary condition, so this should be equal to 0, which implies that xt plus 1 equal to xt, and vice versa. If x bar is a fixed point, then the stationarity conditions must be satisfied. That's straightforward, so let's get that out of the way. Now what happens to lambda, right? If it satisfies the KKT conditions, then g of xt should be less than or equal to 0 for all xt, right? So g of xt should be less than or equal to 0, or gi of xt should be less than or equal to 0 for all I, right? And lambda t should be greater than or equal to 0. So let's maybe write that down. Xt equal to xt plus 1 if and only if gradient f of xt plus dg transpose xt times lambda, this is equal to 0. Okay. Now suppose that, so if lambda t is equal to lambda t plus 1, right? Remember that lambda t and lambda t plus 1, they have to be component wise greater than or equal to 0, because that's what we're enforcing in every step of this algorithm. Right, so each component is greater than or equal to 0. Then what can you say about this particular quantity? So So recall that lambda t plus 1, the ith component, is given by the ith component of lambda t plus delta t times gi of xt, the positive part, right? So if lambda I t plus 1 is equal to lambda I, there are two conditions. One is if lambda I t is equal to 0. Alright, suppose that this is equal to 0, then what can you say about gi of xt? Does it have to be, can it ever be greater than 0, strictly greater than 0? So remember that lambda I t plus 1 is equal to lambda I t. And I'm saying that both of them are equal to 0. Right? Because that's what I said here. That's the proposition. Right? So gi of xt cannot be greater than 0. Can it be equal to 0? Yes, I can set this to be equal to 0, this to be equal to 0, and this to be equal to 0. LHS will be equal to RHS. But I also have LHS equal to RHS if gi of t of xt is less than 0, because I have this positive part over here. Right? So this implies that this is less than or equal to 0. Correct? Okay, which means that constraints are satisfied. But if lambda I t is strictly greater than 0, all right, what can I say about gi of xt? Can gi of xt be strictly greater than 0? So remember that this quantity is equal to this quantity and it's strictly positive. Alright, that's the assumption. So this is equal to this and greater than 0. So can this quantity be greater than 0? Not possible, because the positive part of this would be just lambda I t plus delta t gi of xt, which would be different from lambda I t plus 1. Right? So gi of xt can definitely not be strictly greater than 0. Fair enough? But can it be less than 0, strictly less than 0? That can't be, because if this is not strictly less than 0, then again you will not have the LHS to be equal to the RHS. That's okay. So basically I have a real number here, a positive number here. This is something positive, let's say 2. This is also strictly positive and equal to this. Right? So this is 2 is equal to 2 plus something positive part. So this quantity can't be less than 0 or greater than 0. It has to be equal to 0. Right? But what is this put together? Exactly, it's complementary slackness. Right? You can also argue the other way around. Suppose that it satisfies the complementary slackness conditions, then this would indeed be a fixed point of this set of equations. So this algorithm is nice, this particular iterative algorithm based on minimizing the Lagrangian or gradient descent of the Lagrangian with respect to x and gradient ascent of the Lagrangian with respect to the Lagrange multipliers. If this converges, then it's guaranteed to converge to the correct solution. It's an approach, that's one way of solving for the KKT conditions. You can also prove under certain conditions, you can prove that this algorithm will converge. Assuming that the step size is small enough and you start with a initial point that is sufficiently close to the KKT conditions, again you can derive a similar bound similar to what we did previously for gradient descent. You can prove a similar bound for this as well. But this will probably be just a linear rate of convergence, not a quadratic rate of convergence like we did for accelerated gradient descent. So these two methods are kind of guaranteed to converge under certain conditions, of course. But in many cases, they're a little difficult to work with. For example, if you start with a point that is a little far away, then this particular algorithm is not guaranteed to converge. And at any point, any intermediate step, there's no guarantee that it will satisfy the constraints, which can be problematic at times. So there are other approaches to solving constraint optimization problems. One is the penalty method. All right, so basically you have a constraint optimization problem. Minimize f of x subject to the constraint that x lies in some constraint set f. So these penalty based methods essentially try to convert this constrained optimization problem to an unconstrained optimization problem, a potentially different unconstrained optimization problem. So instead you minimize f of x plus some eta times p of x, where this p of x is a penalty function. So you penalize if you are outside the constraint set, and you don't penalize as long as you're within the constraint set. So p of x is equal to 0 if x satisfies all of the constraints, and it is something that is strictly greater than 0 if x does not satisfy the constraints. There are a number of different ways to choose the penalty function. And what you can show is that if eta is sufficiently large, then if let's say you did something like gradient descent, unconstrained gradient descent on this particular objective function, and you choose maybe a sequence of etas where eta is becoming larger and larger so that you penalize the constraints more and more, then this will eventually converge to the solution. But then there is this the whole host of other problems as to how do you choose the penalty function and how do you choose eta and so on. Right? These are typically heuristically chosen. Another related approach is the barrier method. If you think about the penalty method, basically you're trying to do unconstrained minimization of this particular objective function, and this objective function is guaranteed to be equal to f of x within the constraint set, but it's not equal to f of x outside the constraint set. But it doesn't mean that you're never allowed to go outside the constraint set. It's just that it is something different. Unless the penalty is sufficiently large, you can't say anything about whether you're going to get the right solution or not. Whether the solution to this will be equal to the solution to this or not. It's only if eta is very, very, very large that the unconstrained minimizer for this will be the constrained minimizer for this. Right? So the barrier method does something similar, but basically modifies the objective function within the constraint set as well. So again, you try to convert it to an unconstrained optimization problem, but instead of minimizing, doing a constrained minimization, you minimize f of x plus again some eta times b of x, where this b of x is chosen in a slightly different way. So basically, this b of x is some function, it's a barrier function, and it is chosen such that b is defined in the interior of f. It's well defined in the interior of f, but on the boundary it blows up. It goes to infinity. So for instance, suppose the actual problem was minimizing f of x subject to, let's say, one inequality constraint, g of x less than or equal to 0. Alright? You could choose the barrier method to convert this to minimize f of x plus eta times, let's say, log minus g of x. So what would this do? So firstly, this is not defined outside. If g of x is greater than 0, it's something which is well defined if g of x is strictly less than 0. But as g of x tends to 0, this starts blowing up. So this log is example of a barrier function. Which one? Minus e to the? Minus eta times log of minus g of x. doesn't particularly matter, but firstly, this will ensure that this is convex, log is concave. That's right. As you go towards 0, you want it to tend to plus infinity.
No, because that is equivalently 1 by gx less than equal to 0, right? If you put a minus.
1 by gx, sure. Okay, that's fine. So this is one example of a barrier function. So what you could do is you initialize x at some interior point, x0 within the interior of the constraint set, and then you just run gradient descent. But this, you run into a problem now because the objective function that you're running gradient descent over is now different. It's not f of x anymore. Right? This enforces that you will always lie within the constraint set, but you're modifying the objective function itself. But this will be close to the objective function only if eta is sufficiently close to 0. So you choose a small enough eta. Again, it's a heuristic way. You choose a small enough eta and then run gradient descent on this particular optimization algorithm, this unconstrained optimization algorithm. That will hopefully get you to the constraint minimum. You can run gradient descent. That's what you typically do. Huh. That will never happen, right? So this way, you choose so all of this is assuming you choose a small enough step size. Right? That's something you always have to be careful about. So you choose a small enough step size so that in that case you're sure to lie within the, in fact you'll be in the interior of the constraint set.
So the function doesn't approach 0 because you put a very large value.
Yeah, so the closer you get to the boundary, it will sort of push you towards the interior. It will push you quite hard towards the interior, in fact.
But you should be careful that the gradient step does not lead you into the undefined region.
True, yeah. So you have to, all of this is assuming that the step size is not too large, because that can always throw you out. And it also depends on how fast this barrier function approaches infinity as you get close to the boundary. Right? So
when I iterate, I say get a value of xt plus 1, which makes that log of something negative.
correct, that's exactly the point that he was trying to
Then
make.
I take it as like plus infinity, and how do I change my iterations?
So then you have to go back to the previous iteration and maybe change the step
Play with
size,
the delta t or something.
play with the delta t or something like that. Yes. But one thing you have to be careful about over here is that this does not handle equality constraints. It has to have a well-defined interior. Right? There are other ways. For example, you instead of minimizing this, you put a constraint. You put all of the equality constraints in here and solve the equality constraint optimization problem. And then you could run something like projected gradient descent over this. That's one way of doing it. So again, these are not specific algorithms in themselves. These are general approaches towards solving constraint optimization problems. Depending on what specific problem you have, you will be choosing one of these or some variant of these. So in this course, we've just sort of scratched the surface of what is known about solving constrained optimization problems. But no matter which algorithm you choose, no matter which optimization problem you have, the basic principles are all the same. Effectively, all of them are some variants of gradient descent. Could be mirror descent or accelerated gradient descent. The high level ideas are all the same. Right? But depending on what kind of guarantees you want, depending on what the objective function is, what kind of constraints you have, whether it's efficient to run a particular algorithm, you select one of those. All right? Any questions? Okay, so if not, we'll stop here.